Hello class, Dr. Barnes here. So let's get into the properties of Laplace transforms. Okay, so the first property that we should deal with is let's call this one 1. Okay, is linearity property. Okay, linearity property. Okay, so here if x1, okay, of t has a Laplace transform of x1 of s, okay, and then the ROC, region of convergence, ROC is, let's say, R1, and then we have, let me write the n completely so it doesn't confuse you. So and x2 of what, t, has a Laplace transform of x2 of what, s, and the ROC, here is, let's say, R2. Okay, then what we should have is that a x1 of t plus b x2 of t should have a Fourier transform, okay, of a1 of a x1 of s plus b x2 of what, s. Okay, then we are expected to have this Fourier transforms. Okay, and the ROC should be R1 intersection R2. Okay, so here let's just prove this simple thing. Okay, so the Laplace transform of ax1 of t plus bx2 of what, t, okay, is expected to be equals to here ax1 of t, okay, plus b what, x2 of what, t, is bx2 of t, okay, into e minus what, st the what, dt. Okay, so if we do this one, then we are supposed to have here we are supposed to therefore have a x1 of s plus b x2 of what, of s. Okay, es1 of s plus what, bs2 of s. Okay, which will have an ROC of R1 intersection R2. Okay, so basically that is what it will give us. Okay, that is what it will give us. Okay, because if you should expand here, then you're going to get a x1 of what, t, okay, into what, into e minus what, st, okay, plus, if you can bring the limits. Okay, you can bring the limits, no problem. Okay, okay, so into what, x2, okay, x2 of what, of t, into minus what, st, okay, the t, you can bring the t, okay, the t, all right, here's plus. Okay, so this place, what will it give me? It will give me a x1 of what, s. Here, what will it give me? It will give me, sorry, here is what, bx2 of s. It will give me bx2 of what, s. Okay, then the Laplace transform, okay, of ax1 of what, t, plus bx2 of what, t, okay, Laplace what, transform is what, ax1 of s plus bx2 of what, s, and then our ROC is what, R1 intersection what? R2. So R1 intersection what? R2. So this becomes what? Our answer, our proof. Okay. So now let's go to the next property. Let's go to the next property. Okay. So the next property is called the property number 2 is what? Time shifting property. Okay, what is time shifting? Okay, first, if x1 of t has a Laplace transform of what? X1 of what? S. Okay, and the ROC in this case is what? Let's say R. Okay, is R. Okay, all right. Then what we expect is that if we have time shifting means t minus what? T naught. That is time shifting. Okay, then our Laplace transform here is going to be e minus t what? Naught into what? X1 x of what? S. Okay, x of s. Okay, here our RO what? C. Our ROC will be what? Just R. Okay, so now let's prove this particular property. So now here, Laplace transform of what? X of what? T minus what? T naught is equals to what? Here, minus infinity and then what? Infinity. Here, x of what? X of t minus what? T naught. Okay, x of t minus t naught into what? Minus st what? The t. Okay, the t. Okay, so what we can say is that t minus what? T naught is equals to what? Tau. Okay, t minus t naught is equals to tau. So now, if t minus t naught is equals to tau, then here I can put tau here. Okay, and what will I have here? Here I can have what? T naught plus what? T. Okay, then what I'm going to have is that here integral infinity minus infinity. I'll have x of what? Tau into what? E minus what? S. Okay, I have what? I have here, I'm going to have what? Tau plus what? Plus t naught, or t naught plus tau is the same. Okay, here x of what? Tau. So here will be what? The tau. Okay, here will be the tau. So now here, what I can say is that if I should bring e minus t what? T naught out, I'll have integral minus infinity to infinity x of what? Tau into what? E minus what? E minus s what? S tau. Okay, the what? The tau. Okay, the tau. Alright. So I'll have the tau. So you see that this one is what? Fourier what? This one is what? Laplace transform. That gives you x of what? S. So that I will have what? E minus what? S what? T naught into the Laplace transform of s of x. Because this one, this particular thing I have here is what? Laplace transform for what? X of what? S. Okay. So now, what I can actually say here is that whenever I have x of t minus what? T naught, which is time shifting, then I will have a Laplace what? Transform of what? E minus what? S what? T naught x of what? S. Okay, and the ROC will not change. It will be, the ROC will be as the original, which is what? The same word, ROC. Okay, so if this one were to be Fourier transform, okay, then what happens is that our S here would have become what? J what? Omega, if it were what? Fourier transform. Okay, so now let's go to the next one. Okay, let's go to the next one. Okay, so our next property is property number what? 3. Okay, shifting in what? S domain. The previous one was time shifting. This is shifting in S domain. Okay, so here, if x of what? T has a Laplace transform of x of what? S. Okay, and the ROC here is what? R. Okay, then what am I going to have? Okay, then I'm going to have this particular property. Then I'm going to have EST naught. Okay, EST naught. All right, of what? X of what? T, to give me a Laplace what? Transform of x S minus what? S naught. Okay. All right. So here, what will my ROC be? Okay. So here, my ROC is going to be my ROC is going to be for this one, this particular place. S of S here will give me what? R. And this one, okay, will give me R plus what? R into what? RE into what? S naught. Okay, so basically what is happening here is that this R is from this X of S, and this RE into S naught is from what? This X of what? S naught. Okay, so that's how my ROC will give me. Okay, so let's just prove this simple property. Okay, so here Laplace transform of what? Laplace transform of what? E into what? X naught into X of what? T. Okay, is going to be here infinity minus what? Infinity. Okay, E S what? T naught. Okay, into X of what? T. Okay, into E minus what? ST d what? dt. Okay, so this is what we're going to what? Have. Okay, so now if we have this property, then what we actually need to do is that we can just simplify here and then here. Okay, I can just simplify here and here. Okay, so if I do that, then I'm going to have here infinity minus infinity. Okay, here what I can do is that I can have minus out. I can have E here. I can have minus out. Okay, if I have minus out, I can have this minus, this S, and I can have another what? S. Okay, into what? T. Okay, here is basically I have made a mistake here. Okay, so basically it's ST. But the naught is here. Okay, sorry. So basically it's what? ST, and the naught is here. It's when I was doing the differentiation that I realized. Okay, it's what? ST. Okay, and the naught is what? Here. Okay, so that is why, how come here you see where our RE of what? S naught. Okay, where the naught is affecting. The naught is not affecting the T, it's affecting what? The S. That is why our ROC is what? RE into what? S of what? S naught. Okay, so here, this is what I'm going to have into what? Here is what? S naught. Okay, here is what? S naught. Okay, and then T comes here. All right, and T comes here. Okay, so now then into what? X of what? T into what? The T. Okay, so now if this is what I'm actually what? Going to have. Okay, this is what I'm actually going to have. Let me write these things here. Okay, so now if I have this one, basically what I'm going to get is that you see that basically this and this part, this and this, okay, will give me one Laplace transform, and this one, okay, will also give me another what? Laplace transform. This and this will give me one Laplace transform, and this also give me another what? Laplace transform. So my Laplace transform is going to be X of what? S minus what? S naught. Okay, so now you can see that LT, okay, of what? E S naught into T into what? X of what? T, okay, has this Laplace transform. So if I don't want that, I can just also write it like this. E s naught t x of what? T has a Laplace what? Transform of x of what? S minus what? X naught. Okay. So basically that is how you get it. Okay. And we know the ROC already. So the ROC in this case is what? R plus what? R for x of s. And then x of s naught will give us what? RE into what? S naught. S naught like this. Okay. So basically from here we can also then we can also see that if we have E minus s naught t, then into x of what? T. Okay, then our Laplace transform should also be what? Could also be found. Simply that will be what? X of what? S plus what? S naught. Okay, alright. So basically that is how you can just do this one. Alright. Let us find another Laplace transform. Okay, let us do number 4. Let us find another property. Time differentiation property. Differentiation property. So this is property number 4. So time differentiation property. So what is the time differentiation property? So here, if what? X of what? T has a Fourier what? Transform of x of what? S. And then the ROC here is what? R. Okay. Then if I should differentiate this part x of t, okay, so time differentiating, so I'm differentiating with respect to what? Time, because it's time differentiating. So d over what? Dt, meaning dt is what? Time, differentiating time. So x of what? T, all right, x of t should also have a Fourier what? Transform, okay, of s, x of what? S, okay. And then here the ROC, okay, so here the ROC is going to be what? The same what? R, okay, no change in the ROC. So here we're going to just do it this way to be able to prove it, okay. We're going to take inverse Laplace transform. Okay, we're going to take inverse Laplace transform. Okay, so the inverse Laplace transform actually is given by x of what? T is equals to 1 over what? 2 pi into what? J. Okay, and then I have what? Integral of what? Sigma minus j infinity. Okay, then what? Sigma plus what? J what? Infinity. Okay, and then here I have x of what? S. Okay, into what? E exponent what? St d what? ds, because here is s. Okay, so this is what I'm gonna have. Okay, so now here differentiate both sides. Okay, differentiate both sides. So if I should differentiate both sides, then this is what I'm actually going to have. Okay, so if I should differentiate both sides, then what I will have is that if I should differentiate this part, okay, if I should differentiate this one, okay, basically I'll get x of t. I'll get x of t. Okay, so differentiating both sides. Basically here, then this is what I'm expected to get. Okay, so differentiating both sides, that means that I must differentiate the inverse Laplace what? Transform. Okay, the inverse Laplace transform. So I will actually differentiate this side. So now d of x of what? T over what? dt. Okay, is equals to 1 over what? 2 pi j into what? Into what I have here. Okay, into what I have here. What do I have here? Sigma plus j what? Infinity. Sigma minus j what? Infinity. Okay, so x of what? S. And then I'll differentiate here. Okay, d on what? The t. Okay, d on the t. E S what? T. Okay, the what? The S. Okay, so here I can just do it like this. Okay, so if I do that, then I'm going to actually have 1 over what? 2 pi what? J. Okay, into what? Integral sigma plus what? J. Okay, and then sigma minus what? J infinity. Sigma plus J infinity. Okay, so here, if I differentiate this one with respect to what? T, then I'm going to have S. So I'm going to have S, okay, X of what? S. Okay, if you differentiate this, I'm going to have S. Okay, and then I'll have E S what? T. Okay, E S T the what? The S. Okay, so if I differentiate with respect to this one, this is what I'm going to actually have. Alright, that's what I'll have. But if you take a look at this one, you see that the whole of this particular equation that I have here, the whole of this equation here, okay, except for this S, is what? Is what? Time difference. The whole of this equation here, except if I remove this S from inside. If I remove this S from inside, then the whole equation here is representing what? Is representing what? X of t, which is this one. Is representing what? X of t. And I know that X of t is a what? Inverse Fourier transform for what? X of S. Okay, inverse Fourier transform for what? X of S. So I can remove this whole equation and write what? X of what? T. Okay, so I can remove the whole equation and then write X of t. Okay, so basically this is what I am actually saying. What I am saying is that I hope you can see. What I'm saying is that X of what? T is equals to 1 over what? 2 pi what? J into what? Sigma plus what? J infinity. Okay, sigma minus what? J what? Infinity. Okay, so here I have what? X of what? S into E S what? T d what? The S. Okay, so this whole equation here, if I remove this S from inside, it will become like this. And this is what? X of T. Okay, so basically I can write what? S into what? X of what? T. But I also know that this X of T is the Fourier transform, okay, for what? X of S. X of what? X is the Fourier transform for X of S. Okay, so then what I want to do is that I'll write here X of what? S. So I'll write here X of what? S. And then I'll bring this S. Okay, which is my Fourier transform for what? D over what? Dt. Okay, into X of what? Into X of what? T, which is the what? Laplace, which is the Laplace transform. Okay, which is the Laplace transform. Okay, so it's proven. Okay, so it's proven. All right. Okay, it's proven because you can see that this is what we set out to achieve. Okay, and we have been able to achieve it. And our ROC is what? R. Okay, there's no change in the ROC. Okay, all right. So it's proven. So I'll see you in the next class.